Welcome everyone to this talk. Welcome to everyone who is watching on the live stream or listening. It's great to see you in this big hall. Our next guest is Fefe. Fefe is a security consultant. He's also the co-founder of the company Code Blau. It's specializing in security concepts. And Fefe belongs to this CCC inventory, kind of like the downtime of the wiki. For those who are not from Germany, Fefe has a little blog in Germany. A little and pretty blog.
Really tiny. Not many people read that, or?
Can we change the subject, please?
I do want to say, though, that this blog is the only website that comes up when you go into the Berlin U-Bahn in the metro. So this is the fastest loading time of all websites. And Fefe will talk today about programs that sandbox themselves and why that is a good idea. So in this talk, check your privileges, how to drop more of your privileges to reduce attack surface. Please help me welcome Fefe.
Good morning, everyone. Thanks for showing up. So this talk is about how you can write your own programs. So even if they are exploited because you have a bug in them, the damage is still limited. And the idea for this is pretty old. It's probably older than when I blogged it in 2007, but this is the first mention of it I found in my own blog. So I've been working on this for a while, or at least thinking about it. And now the building blocks have come into place, so I can show you how to do this now. But before we start, let me make one thing clear. This is not something you do instead of making your code good in the first place. This is something you do after you make sure the code is good. It's like an insurance. It can save your ass, but if you're negligent, then they won't pay you out, right? So basically, I'm trying to show the problem I'm trying to solve first. So basically, when you plan software, you think of it like this. And when it's written, it's more like this. Basically, we depend on lots of code with bugs in our daily lives. And many of those bugs are security bugs. And if someone tries to attack something, it's usually something that has more access rights than the attacker in the first place. And when the attack succeeds, the attacker has gained some privileges in the system. So how can we solve this problem? And the obvious idea is that, well, make sure there are no bugs in the code. It's not that simple, it turns out. The second obvious idea is to reduce exposure of your code. Make sure it's only in the intranet, as a typical thing people used to say for a while. Make sure it's only reachable via HTTPS after authentication, so you know only people with accounts can attack you, which may not lessen the burden a lot if you're, say, an email provider, because everyone can have an account. Or maybe it's an internal microservice and it's not visible from the internet, or it's behind 7 proxies. Or people can come up with pretty wild scenarios. But no matter what you do, all you can do is reduce probability of a hack. You don't rule it out entirely. So even if you do all this, you can still get exploited. So what can we do to make exploitation harder? This is where most of the research right now is focused. You can have non-executable stack, which is pretty standard these days. You can have cookies on the stack. You can have a hardened heap. All those are standard too. ASLR and position-independent executables. ROP protection is kind of the new thing that people are trying to make a standard. You can ban dangerous APIs, which is a good idea. You can train developers. You can have a bug bounty. That is a good idea too, if you have them cache lying around. You can run the code on some architecture that you hope nobody knows how to exploit. But in the end of the day, it's just a reduction of the risk. It's not actually, you can't really sleep sound. And the idea I'm going to talk about today is that maybe you can put your code in a straitjacket and drop privileges so much that even if someone can find a bug and exploit it, the access they gain is minimal or non-existent. Basically, the less the code can do, the less the attacker can gain by attacking it. However, there's a massive difference between what the code can do and what the code actually does. So I'm talking about what the code can do. This is not about, well, I'm not writing files anywhere, so I should be safe. No, if someone gets code execution in your process and that process can write somewhere, then that's a problem. So this is not about what your code actually tries to do, but what it could do with the privilege level it's running as in the operating system. The post-exploitation attacker is not limited by what your code was trying to do. This is very important to understand. Basically, if you run something like, say, ping, it's a setuid root program on Unix, then if the service, or like an HTTP daemon or any system service, basically, it's usually running as super user traditionally, and the super user has all the access in the system. So this is really bad. The obvious first step is to reduce this a bit. So this is what the super user can do. The next step is you drop privileges, so you run as a normal user in the system, and you still have a lot of privileges. But usually it's better. And this talk is about maybe we can drop privileges some more. And the service can only really do very tiny things in the system. That's the idea. Common patterns for achieving this are the app drops privileges, and then you do all the really hard and dangerous stuff in the beginning, then you drop privileges, and you hope that the bug that the attacker will find is in the code after you drop privileges. And this may be a sound assumption, but it may not be. So this is kind of risky. But it's a common way to approach this. The next way to approach this, I'm going to talk about all of this in detail, is called privilege separation, when you split up your process and you move the dangerous part in a separate process and make sure that process can't really do anything. And another thing that's usually done is if you're really helpless because you can't trust the app and it's really big, you put it in a VM or maybe a container or a jail, and you hope that these mechanisms will constrain the explosion a bit. But maybe the app can confine itself too. And this is an idea that's pretty new, I think. It's only been gaining traction in the last few years, as far as I know. And then the broker service, which is a common idiom. You split up your process and you make sure, for example, the left half of the process can't open files, but it can talk to the right half, and the right half can open files. And if the left half wants to open a file, it asks the right half. And this is very small piece of code, so we can be more sure that it's safe. Dropping privileges is generally understood as dropping them for good. So the idea is you can only go down in privileges, you cannot go up again. In practice, that's not as easy as you would think. So traditionally what we did is we only look at dropping privileges for privileged processes. We say, well, if it's running as some user ID, we don't care, that's already pretty safe. So this is where traditionally the idea of dropping privileges comes from. setuid programs or programs starting as root. And common examples of this are ping, because it needs raw socket access and it's restricted to the super user. And the X server used to be running setuid root. Nowadays there's other ways to do this because it needs access to the raw graphics hardware. And the third is Xterm, which used to be setuid root because it needs to create a TTY, and only the super user should be allowed to do this. Basically, the idea again is to do the privilege stuff first and then drop privileges and hope that all the attacker can do is attack you after that. Privilege separation, I think the term comes from the OpenSSH people, or basically the OpenBSD community has imprinted this term. They invented the concept, as far as I know. The idea is to split up your process. So let's say you have this hugely complex crypto and parsing code that does the SSH low-level protocol parsing, and you think it's safe, but you're not really sure. So you put this in a separate process, and that process is confined to a small empty part in the file system. And you make sure it can't do anything except parsing the protocol. And then if anything blows up, it's only that part that blows up and not the whole thing. The whole thing can do diagnostics and say, oh, someone tried to hack me. The other idea was the admin confining an app in a jail container or VM. And basically this works on a whole system level. There can be more granularity, but usually what you do is you take the whole thing and put it in some kind of environment, restricted environment, and this is done by the admin, not by the app itself. The problem is if you have some kind of rule set, there's several implementations for this that I'm going to show. If you have a rule set, this program can do this and this and this, but nothing else, how do you get that rule set? This is surprisingly difficult if it's not a trivial program. And for simple processes, it can be done, and it's reasonably easy, but that's not the ones we're worried about, right? So we think about stuff like Firefox. Also, in my opinion, you can't expect the admin to come up with a set of rules to confine a program. It's not the admin's job to understand what every eventuality, every error code path in this app does. You don't even know if you used all the regular functionality in the program usually. Are you sure you clicked on every button in Firefox in your lifetime? And you would have to do that to make sure that your profile is complete. So usually what happens in this kind of scenario is that there's some obscure error path you haven't seen yet that the program would have been able to handle gracefully. For example, disk full or memory allocation fails. And then suddenly the program behaves differently, and that's a violation of your profile, and the whole thing blows up. So it's very hard to come up with this profile. That's why I think it's a misguided idea to do this. You can still do this on top of actually having the program sandbox itself. It's an orthogonal idea, but I don't think this should be the only thing we do to constrain applications. The other idea is that, well, maybe not the admin is doing this, but the distro guy, the Debian package maintainer does this, and I don't think that's a good idea too. You can't really expect them to do this. They're basically, students doing this in their spare time. But how would they have a year to study Firefox and come up with a profile? So the central idea of my talk is the app confining itself. Basically, think it's a werewolf chaining itself to the wall before full moon to make sure that even if something happens, I'm still confined here and don't do damage. So basically what you do is you make sure there's a little part in the file system, only the stuff you really need, and you can only access that part. There's several ways to do this. I'm going to talk about them. You cannot open files outside this part of the file system, or maybe you can't open any files at all. If you don't need, ping doesn't need to open files, you would think. But it turns out it does for DNS lookup. So it's all the devil is in the details here. It's easier to talk about it than to actually do it. Another thing that's usually overlooked is that even if you can't access the file system, there's still lots of stuff you can do. System 5 IPC is its own namespace, for example, which means you could access shared memory from other processes if they use System 5 IPC. Or you can send signals, just kill processes. Or you could use ptrace, which is the Unix debug API, to attach yourself as a debugger to some process outside of your environment. So it's not enough to limit the file system access. There's more stuff you can do. So the main thing you should take away from this is that you probably have to restructure your application the way it works. You limit what the main application can do to reduce the part you really have to be sure about to the broker service, and the broker service gets messages from the main program, stuff like, I want to open this file for reading, or I want to open that file for writing, and the broker service can do additional checking aside from what the operating system is doing anyway. And to make this worthwhile, you have to make sure that the main process does not have any way to actually, or any access rights to access the file system itself. And there are several ways to do this I'm going to talk about. The problem is that sometimes there's ways for the main program to trick the broker. So if you just do a separate process and it's running under the same user ID, for example, then you could attach a debugger to it. The main program, if it's being hacked, could just use ptrace to override the code execution flow in the broker and just make it do anything at once. So this is more tricky than I'm letting on here. So let's get to the dirty details. First, the old school way. This is what ping is supposed to do, or like let's say in the 90s. This is what we used to do in the 90s. Basically what you have is you have two UIDs in the process data structure in the operating system. It's like some struct somewhere in the kernel, and it says, well, you have the real UID and you have the effective UID. And if the program is run is setUID, then the effective user ID is the one that the binary is setUID to. So that means if the program does anything, the kernel doesn't actually look at the real UID, it looks at the effective UID. So let's say you understand this and you want to drop your privileges, then you could just say set effective UID to get UID, to drop back to the real user ID. And you would think that's enough, right? And it turns out, no, it's not enough, because at some point there's a third UID that allows you to go back even after someone tried to drop privileges. And this is, at some point, the various versions of Unix and BSD diverged on this point. So it was, for a time, it was pretty hard to write code that does it right. At some point, a new API was invented. It's called setResUID. You can set all three user IDs with this, and that's actually okay. That's a good way to drop privileges. However, it's not enough to do this. You need to check the return value. And if you don't, things can go badly. Also, it may not be enough to reset the user ID. There may be group IDs that are privileged too. So the devil is all in the details here. So what can happen if I'm the super user and I want to set resUID to some user ID? How can this ever fail? There is system-wide limits, resource limits for UIDs. So there could be a limit that there can only be 10 processes for a given UID. And if that UID already has 10 processes running and root is trying to drop privileges to that UID, then that will fail. And if you don't check the return value at that point, you might as well not have dropped privileges in the first place. So if you do any of this, be very careful to understand all side effects and things you have to watch out for. It actually used to be even worse than that, because there was a different call set reUID that looked like it does the right thing, but it doesn't. And in many programs today, you find backwards compatibility code if set resUID is not found by configure. And in many cases, that code path is pretty bad. So my advice is, if someone tries to build your program on a system that doesn't have set resUID, then just fail the build. We need to get this everywhere. There's no way. Even so, well, let me give you an example. This is from an Apple security advisory a while ago. It says basically the issue was that the set regid system call failed to drop privileges. Well, that's what it's there for, right? So very careful with this. Actually test it works, and make sure you check all the return values. So, but have we actually dropped privileges? Let's say we are ping and we get a raw socket in the beginning, and then we drop privileges, and then someone attacks us successfully. Then maybe we're not running as root anymore, but what happens if all the attacker wanted was the raw socket? We still have that. So dropping privileges is more than going back to a UID. Also, the concept of, well, we do the dangerous stuff first may be more difficult than it looks like. So for example, what about parsing command line arguments? You can have bugs there. Actually, the X server used to have a bug there. And they said, well, we have to do that first, and then we do the hardware stuff, and then we drop privileges. So this is dangerous too, parsing command line arguments. And what if the attacker is using environment variables? What if the bug is in the dynamic linker? There were examples of this too. So that's before even your main is running. So dropping privileges it's a harder concept than it looks like. And if all the attacker wanted, as I said, is the raw socket, then there's not much you can do. The code still has to be good. So let's talk about privilege separation. Let's say you have web servers and it wants to convert uploaded images to, let's say, create thumbnails or make sure it's all a JPEG without metadata or whatever. Want to remove EXIF, something like that. But the way to do that would be to support all these image formats, and nobody wants to write that code. So what people do is download libraries to do that, and those are big pieces of code. Many of them have had security problems in the past. There's basically not many reasons to trust them now. So that might be a good idea for privilege separation. You move that in a separate process, and that process has no privileges, and it doesn't have to access the file system in any way because it gets the image over some socket or pipe or whatever, and it gives you the result back over another socket. So this could be locked down. There's a difference between using all the libraries directly and using some kind of wrapper around them, which is even more popular, something like ImageMagick. In any case, no matter how you do it, it's a huge code base that shouldn't really be trusted. So if you do this at some point, that might be a good idea to think about privilege separation. So the idea is to move all that image manipulation stuff in a separate process and lock that process down. So by locking down, what do we mean by that? And so the obvious things are the file system access, obviously system 5 IPC, other processes, inter-process communications. Make sure no new channels of IPC can be opened. Only the ones you gave the process when you created it can still be used. You want to limit network access because if the attacker can't get a shell, then maybe it wants to create a little shell on a network socket. Even if it doesn't have access to bin shell, and that might still be bad. That needs to go away. Maybe there's a routing problem, so this service is only supposed to be a microservice that's visible from your one host in the DMZ, but it has a default route somewhere that doesn't need to be there. So maybe that could be locked down too. There's many ideas what you could try to lock down. Common approaches for this is either namespaces or a prison and a guard. So the namespace idea is that you put together some kind of fake file system that looks like a real file system but only has the parts in it that the process really needs. And that fake file system then becomes the actual file system that that process sees. This is one of the ways you can do this. And usually stuff like etc hosts or etcresolve.conf, stuff like that could be used if the process you're trying to lock down uses DNS lookups, for example. So these kind of files you would need in your fake file system too. And if your fake file system is on a var jail1, you would have a file like var jail1 etc hosts. The namespace concept can also be used for UIDs and PIDs. So the difference here would be if you have something like a container, and in that container there's an init running, would that init have the PID1 or not? If you have more than one jail, can you have more than one PID1? So this is a detailed question that may not matter. Maybe you don't even need an init in your jail, but if you have a namespace and every container has its own PID namespace, then there is no risk that any interaction like kill or any signals, any ptrace, anything that takes a PID could ever affect anything outside that jail. The other approach is to have some kind of prison. The BSD, FreeBSD came up with the name jail for this. You have some kind of Unix permission checks during open. This is done on Windows the same way. This is an old concept. If you can do open, you get a file descriptor back, and when you do read and write on that file descriptor, even if you at that point you couldn't do the open again because you drop privileges, if you have a file descriptor, you can still do what you were allowed to do at the time of the open. So all the access checks are actually done at open and not at read or write. All read or write checks is if the open asked for read or write permission. So the idea would be that you disallow the open in the first place in the part you want to restrict, and then you have some kind of guard, and if the code that you want to restrict needs an open, it can talk to the guard, and the guard or the broker service says, well, this open, yeah, okay, etc hosts for reading, that's okay, but etc hosts for writing, that's not okay. So this is the other way to do this. You can do pretty much the same thing for sockets, and as long as the end result is a file descriptor, it can be passed between processes using Unix domain sockets. So descriptor parsing, the concept is easy, but how to do it is actually pretty crafty. And I would advise against trying to do this yourself. Go find some code that does it. For example, you can use mine. It's available in this library. This is pretty hairy. You can look at it. It's like an if-dev desert. It's really horrible. I mean, you can try, but it won't run on some kind of operating system you never heard of, and it's bad. So it's just 3 lines of code basically, but it's different 3 lines of codes for almost every flavor of Unix out there. So it's pretty hairy. But if we abstract that away, then it should be okay. So how do we restrict file system access? The old solution is called change root. What you do is you create an empty root-owned read-only directory, var jail or var empty or whatever you want to call it. And then in the service you say change dir to that root, that empty directory, then you close all the open files. You say change root to the same directory, and then you drop privileges. Because if you drop privileges first, change root cannot be done. Change root needs super user privileges. So this is part of the stuff that needs to be done before dropping privileges. So let's say you do this, and then the process tries to open foo. Then this foo will be relative to the current path. That is obvious, but if you try to open /foo, the // doesn't work, because that's the one thing change root makes sure it doesn't work. Or if it's a symbolic link that contains // that also doesn't work. So you can't escape from this part of the file system unless you have an open descriptor that already points outside the file system. So that sounds pretty peachy. It's all rainbows and unicorns, but no, it's not. You can escape a change root jail if you are root yourself, because then change root does not nest on Unix. So if you do a different change root while holding a file descriptor to your change root, you're out. This is the code that does it, just so you have seen it once. So if your process inside the change root environment has or can obtain a handle or descriptor to a directory outside the jail, it can escape the change root, either with change dir or f change dir in this case. So that's f change dir is the second way. Change root itself does not change dir. You have to do both. If you don't do both, then it's ineffective. And you need to check the return values again. Even if you are confined to a change root jail, all that does is limit file system access. Socket and signals and stuff still works, so it's not a good solution. It only is for file system. It's not comprehensive. You need to do more. More trouble with change root is that library functions might access their files without telling you first. The most notorious is the DNS APIs get host by name. Depending on the operating system, they may try to open a ton of files like resolve.conf, resolveconf.conf, ns. whatever. So you have to look at what the libc you're using actually tries to open here too, and make sure those files are in the change root jail too. Particularly troublesome for this is if the program you're trying to jail isn't written in a compiled language, but say Perl. And Perl may try to open some other like modules. If the program starts with use something, some kind of Perl module, then Perl will try to load that, or Python is the same thing. So scripting languages are pretty tricky. You would have to have all this Perl code in the jail, in the change root environment too, so Perl can load it. And at that point you risk that someone in the jail could modify those files, right? So the file permissions have to be carefully watched. And even worse, usually the way to put the files in the jail is to hard link them. So if you do a hard link and someone modifies the file in the change root jail, that also modifies the file outside the jail. So even if they don't manage to leave the jail, they might still compromise your system. So you have to be very careful about this. So let's get to the solutions different operating systems have for this. One of the first ideas, and I think it's a pretty good idea, is the BSD secure level. So it basically the same idea as I talked about inside a process. You do the dangerous stuff first, like mounting file systems and doing a file system check. Those need to be able to access a raw disk device, a block device. But after you do file system check, maybe you don't need it anymore. It's a production server, so you might as well turn off the capability in the whole system to open raw block devices. And this secure level can do this. Basically, you can only increase it, only root can increase it, and nobody can decrease it without rebooting. That's the idea. That also means you have to disallow access to devkmem and stuff like that. And secure level does that too. Then I talked about change root. Jail is something like change root on steroids. A jail has their own file system root, and additionally you can set IP addresses for different jails. So in the end you can have a root user in the jail, but without the problems that a root user in a change root environment has. So the root in the jail isn't actually considered root in the whole system. It's like a middle thing, and there's some kind of namespace stuff. This is still in progress. Jails are being extended right now, basically. So keep a watch on the capabilities of jails. They're still being worked on. The admin that sets up those jails can specify, for example, if system 5 IPC access is allowed, or raw sockets are allowed, and things like that. So this is a pretty good thing. And it has been used for building a container style hosting on FreeBSD for a while now. One of the problems with jails, well, maybe it's not a problem, but it makes me feel a bit uneasy, is that there's no actual namespaces. It's like a flag on the process. They extended the struct in kernel for a process to say this is relative to jail 5. So theoretically you could still say kill PID 5 and PID 5 is outside your jail, but there's a check for that. But it still means there has to be a check at every place where you do something with PIDs in the kernel. So I think it's a bit risky, but apparently it's pretty stable and I'm not aware of any issues they had there. PID1 is always in the host, not in any of the jails. If you try to kill PID1 inside a jail, it fails because PID1 does not belong to that jail. That's how it works. So it's like a namespace light, you could say, maybe. But it means if there's two processes in different jails, they can't have the same PID. That's like a slight info leak. No, it's not clear how much of a problem that is, but just to understand how that works. So let's get to the APIs to restrict what a process can do. Capsicum is the FreeBSD way for this. And this is actually a pretty neat API. The whole idea is that you split off a broker service and you use Capsicum to make sure that all global namespace accesses like open file or create socket fail. And the only way to get descriptors to files you want to open is by going through the broker. To make sure that there's some more restrictions actually in Capsicum. So for example, you can say ptrace is not allowed, or you can say socket operations are only these socket operations are allowed. So you can have some more fine-grained control, but it's not completely fine-grained. You can say, for example, mmap is disallowed if you wanted to. OpenBSD came up with an API called tame. The idea is similar to Capsicum, but it restricts some more. My problem with this API is that they have these flags that they needed, and if you need some other way to restrict the process, you can't. All you have is the flags that they provide for you. So it's not programmable, you could say. It's not as flexible as Linux. But if all you need is those flags, and for most people it should be enough, then it's actually not that bad. The problem is that these are defines. So if you want to support different versions of OpenBSD, then you have an ifdefhell. If this flag is available, then use it, otherwise not. So it's portability is a bit bad. It feels a bit like a kludge to me. And the OpenBSD people agreed, so they have a new API now. It's called pledge. And what you do with pledge is you basically the same as the flags, but you put it in a string. And that string is then parsed by the kernel, and if you try to pledge something that the kernel doesn't understand, then there's no ifdef hell. However, the kernel needs to parse strings now, which is also dangerous. So I'm not sure if this is actually an advancement over tame, but and it's there. There is one pretty good idea in pledge that is in no other system. You can also give a list of paths, and file system accesses will only succeed if the file name you're trying to open is in one of those paths. So you don't need to set up a jail or a change root environment. You can say, etc host is okay. Otherwise, my home directory is okay. But all others /tmp is okay. Like you have that kind of list, but my program never needs to look into user bin, for example. You could say that in pledge. That's a pretty neat thing. I would like to see in the other APIs too. So let's come to Linux. Linux has a pretty early concept of capabilities that was from the time when we didn't think about restricting more than dropping privileges. So the idea with capabilities is instead of dropping privileges, we make sure we don't give you privilege you don't need in the first place. It never really took off. So the idea was you could have a ping that doesn't really have super user privileges. It just has the part it needs to create raw sockets. It couldn't, for example, access the disk device or something. Never really got anywhere as far as I know. There's a combined thing that's available on OpenBSD and Linux. It's called systrace. It's also pretty old. The idea is that you have a system-wide profile that says, for example, ls can do opendir, readdir, readlink, these are system calls, and write, because it needs to write the output to send it out. But if it tries to do anything aside from that, an alarm is raised. That's the idea with systrace. However, the profile does not come with the program, and the program cannot set its own profile. This is something the admin provides, or that's provided at installation time. This is what a profile looks like in practice. You don't need to read the fine print just to show you basically what to expect. It's a text file. So systrace, the problem is, where does the profile come from? So, and the answer is, well, the admin has some kind of training mode. And I talked about the problems with that earlier. I don't think that's a good solution, because getting coverage from a program you wrote yourself is already hard. And most people can never get full coverage with their unit tests. How do you expect the admin that doesn't know the code to do it? So I think it's a bad idea. Then there's a kernel patch series called GR security that offers features that are conceptually similar to systrace. It's not part of the stock kernel, so I'm not advocating it here. I think if you want to have this kind of thing, it should be in the stock system and not need any external stuff. And it cannot be used to self-sandbox. Then there's SE Linux, that's also pretty well known. It's conceptually the same as systrace, a little more powerful, but again, can't be used to sandbox yourself. AppArmor is another not invented here type of thing, does a similar thing, also not used for self-sandboxing. And the actual API for Linux you would use to sandbox yourself is called seccomp filter. It's based on seccomp, and this is a startup business model from 2005 where someone said, well, you could sell your spare CPU cycles for, say, scientific computing and cloud computing or something. But since you can't trust foreign code, we'll make sure that the foreign code can't do anything. And it didn't catch on, but on this basis, they invented Mode 2 or seccomp filter. And it uses Berkeley packet filters with, who here knows what a Berkeley packet filter is? Okay, pretty much, it's more than I expected. It's a bytecode VM, basically, it's really horrible. It's a stack machine, very limited instruction set. There is tooling, but you have to look for it, and it's still pretty horrible. But the Linux kernel recently got a JIT for it, so they figured it's fast, we should use it more. This is what a program looks like in TCP dump, which is what it was actually intended for. If you say port 22, then there's a little bytecode compiled that looks at the packet and says, okay, this is IP, this is TCP or UDP, and there is a port 22. So it's pretty gross. And the idea with seccomp filter, seccomp mode 2 or seccomp filter is that instead of a packet, you give a memory buffer that contains the syscall number and all the arguments to the syscall. And then you can write a little program or bytecode that looks at these arguments and says, no, this syscall number is not allowed. There's some more details going on, but if it boils down to this, you have some, it's macro hell and it's really horrible, but I thought you should see it at least once. You would do something like allow syscall open, allow syscall exit, and that's it. This is the easy mode when you don't look at the arguments. There's some trickery that was a security problem in seccomp filter initially, where you would have a platform that allows different kinds of binaries, 32-bit and 64-bit, so you have to do an additional check, but never mind that here. And then you construct a program like this. You have all these BPF jump or BPF statement. You see BPF LD, for example, is a load, and BPF jump is a conditional jump. BPF red says, okay, program is finished here. And you set it up with PR control, which is, as far as I know, a Linux-specific syscall. The plus side is that it works. And if you abstract it away, it doesn't even smell that bad. It's actually quite efficient because of the JIT. And it's reasonably powerful. On the contra side, what the hell were they thinking? I mean, if you expect people to write code like this, then the complexity of the checking code shouldn't approach the complexity of the code you're trying to lock down. Otherwise, there will be bugs in there. There's all kinds of warts if you try to use it, because for historic reasons, there's different ways to do many things. For example, exit versus exit group, or mmap and mmap2, all kinds of stuff. And in the end, what you usually do is you allow both, even if only one of them is called, because they do the same thing. But it's all the stuff you need to know to use seccomp filter. And for mmap, there's the worst problem, because mmap has more arguments than there were free registers on IA 386. So the first mmap version of this, the first version of the mmap syscall didn't actually use the registers, but it used a pointer to a buffer, and you can't inspect that buffer from seccomp filter. So if someone uses the old mmap, there's no way to use seccomp filter to restrict that. Look at the arguments. So this is bad. Unfortunately, glibc hasn't used this in a while, so you should be okay. If you want to inspect arguments, it looks like this. So in this case, we have open, and we want to make sure only open for reading is allowed. So, I mean, it's pretty ugly, you can see that, but you can attempt to abstract that away. So let's say I want to allow open, but only for etc resolve.conf, which is a common thing you might want to do. Can't be done with seccomfilter because you can't inspect memory. And you may be asking why don't they allow that? And even if it could be done, it would still be insecure. And you think of this scene. If you do the check first and say, okay, this is etc resolve.conf, and then you allow the open syscall to happen, then there's a time between your check and the open where another thread of the same process could change the buffer. So even if they allowed this check, this wouldn't work. So you can't inspect buffers with seccomfilter, and it's a good thing. If you need to do that, you need to do a broker service, basically. So there's some things you could attempt. So for example, you could lock down mmap and say it has to be a read-only page for the argument, or only this address is allowed, and when I set up the seccomfilter, then only that address is allowed as an argument. But it gets really hairy, and I wouldn't advise for it. So if we think about this, for example, mprotect would be the syscall to change a read-only map to a read-write map, so we would have to disallow that too. But you would have to make sure that if someone calls munmap on an overlapping area, that doesn't work, so it gets really hairy really fast. So let's say don't do this. However, fortunately Linux is not Unix, and doing this in the broker is comparatively easy because you can just do an open in the broker and then look at the full path of the file via the proc file system. So that would be one way to do it, basically. Or you use namespaces, which is probably the better way. So yeah, basically, this is how you would do it with a broker. You have to ask yourself the question, have we really locked anything down if we do all this trouble? Because let's say in the end you have something like Firefox, and there's a save as function in Firefox. And the idea of that is to allow writing anywhere in the file system. How do you lock that down? So even if you put that in a broker service, someone who attacks Firefox could still, well, it couldn't write, but it can ask the broker service for writing. And since it's the idea to allow writing everywhere, the broker service would allow it. Or let's say not save as, but open local files. You are allowed to say open and give a file to Firefox. So the broker would have to allow opening files. And that means even files that may not be suitable for Firefox, like your SSH private key, Firefox can open those, right? So even if you lock down Firefox, and Firefox is just a metaphor here for complex processes. Let's say MySQL is the same thing. MySQL should have permissions to open files because it's needed for some functionality. You may be able to lock that away in special cases when you don't need it, but you can't just do that, for everyone. So it's a problem that you may be able to lock down more if you know more details about your application. And that's one of my arguments, because the admin usually doesn't, the programmer does. The big elephant in the room is kernel bugs. We have a high-profile kernel bug around every 6 to 12 months. And if we rely on some security mechanism like namespaces or seccomfilter, the next vulnerability might be in there. It's complex code has bugs, right? So the expectation is most unfound bugs are in obscure places. So my example for this would be X25 socket handling, because nobody uses that anymore. There are probably still bugs in there because nobody cares. If we lock that away, we gain something. So there is a value not just in restricting permissions, there's also value on top of that in restricting kernel APIs that are visible to the program, and locking away APIs that might have a problem in the future. That is also a win. Even if we don't gain anything tangible now, it's insurance against the future. So the first rule of seccomfilter is block future calls to seccomfilter. So as an example, I tried to lock down my ping implementation to get a handle on all this functionality. And so the first thing you do is you get a raw socket and you drop privileges. And after that, you want to lock down what the attacker can do. So before you do command line parsing, right? So you lock that down. The documentation says if you apply 2 filters with seccomfilter, then both are applied. So I thought, oh, that's good. I can do several stages. So the first stage drops stuff I never need. But file system access, I can only block after I did the DNS lookup. And that I can only do after I pass the command line. So I have more privilege than I really need during the time I parse the command line. So I did several calls to seccomfilter, and I found out that it didn't work as advertised. So this is a caveat that you should know. I could install a filter that disallowed further calls to seccomfilter twice. So it obviously didn't get applied. So have a unit test for your lockdown mechanisms too. On Windows, theoretically you can do this, but it's so hard that I would recommend against it. If you are really dead set on trying to do this on Windows, go read the Chrome sandbox implementation. It's open source. It's really hairy, and I wouldn't feel safe if I had any of that code, to be honest, in my project. So if you can at all, do avoid Windows for this. You might, the way to do this might be to use their app lockdown, then it's not your fault if the lockdown isn't good. But trying to do this yourself is not a good idea, I think. So to sum it up, I think we're in a pretty good place from the functionality because we can do most of the stuff we want to do on Linux, FreeBSD, and OpenBSD at least. Fine-grained lockdown is possible, but it's very hard and fidgety. On the other hand, if we write code, that code is usually also hard and fidgety, so I don't think that's much of an argument. If you are a paranoid software author, you can sacrifice some performance to gain more security. The trailblazer here is OpenSSH, and their sandbox source code should be something you study if you want to find out how to do this. Personally, I feel I can sleep well at night knowing that I locked down my code with this stuff and tested that the lockdown actually works. Your mileage may vary. Closing words, use this in your own code. I think this should be the shipping or deployment equivalent of having unit tests. Everyone should have this. If your process is too big to apply this reasonably, then split it up. I think we should strive for a future in 10 years or something where nobody ships software that doesn't have some kind of lockdown mechanism like this. If your code fails after updates because you lock down tightly and it needs more permissions now, then you were doing it right. Because that means your lockdown was very precise. That's how it should be. So there's work involved. Don't get me wrong, this is hard work, and you need to be very concentrated, and you need to check whether you actually achieved what you wanted, but you can do it, and I think you should do it. Any questions? I think we only have 5 minutes, so.
So we have about 8 minutes.
You can always send me an email, or I will be available here in front.
Let's start with a question from the internet.
Okay, the first question from the internet is if you saw the talk on Cloud API, and what are your thoughts on this?
On what? I forgot.
The talk on Cloud API.
Which API? Cloud API. Oh, Cloud API. I didn't actually see the talk, I'm sorry, but I will look the video. I think they're basically using the same mechanisms. I still wouldn't trust the announcement they make that you can run untrusted code if you lock it down. I wouldn't go that far, but basically what they do is the same thing. They use these mechanisms to lock down, and that's the way you have to go if you do cloud computing.
Mikro 1 bitte.
So what was your exact criticism of the SecComp2? Is it the design of the virtual machine, the instruction set, or the fact that you have to use these macros to write your code?
Well, actually, it turns out you don't need to use the macros. There's a library that abstracts it, but since the whole reason to use this stuff is because you don't trust your libraries, I didn't mention it. I think you shouldn't be using libraries to abstract this away. My criticism is that you need too much context to use it. So the OpenBSD API is pretty good in this respect. It's very easy to use, and there's not much you can fuck up. And I would hope that there's some way to do this more easily in Linux too.
Mikro 2, bitte.
What is your take on XDG app for application sandboxing?
On which one?
XDG app, the one the GNOME project is doing for larger applications that normally don't run as root, but as a normal user.
I haven't actually looked at the details there. I don't know, sorry.
Okay.
Microphone 4, please.
So my question is, all these privileged dropping happens at runtime. You have to code it into the binary yourself. Now there are some processes, tools where you know that right from the beginning you don't need certain kinds of accesses. Wouldn't it make sense to have kind of like the seccomp binary code be in a special section in the ELF binary and have loaded by the kernel right from the beginning?
Yeah, that would be awesome, but we don't have the tooling yet. So if someone would hack that would be nice.
Another question from the internet, please.
Yes, the question is, what do you think about running a target application in like hardened Docker with like LSM, seccomp, and C groups?
Yeah, I mean it's a good idea. However, how do you know that? I mean, Docker doesn't really lock down everything. They use namespaces, which is good, but if you have a kernel bug, there's more you can do to avoid it. I mean, not in all cases, but I don't feel as safe with Docker than I would feel with Docker and an application that also does seccomp filter to restrict itself more.
Microphone 3.
Thank you. Everything you explained looks like I need to call all these features from C. Is there some way to call those restriction APIs from some high-level type-safe, memory-safe languages?
Probably. However, you need insight in what the runtime of those languages does, and that's a whole other can of worms. Usually from more high-level languages, you can always call C code in some way or other, so it should be possible.
Microphone 2, please.
Yeah, my question kind of relates to the previous one. So you mentioned resolveconf being read during name lookup. So is there any attempts to kind of make this modular when you have a library and you at least need to document or specify in some way what this and that call needs in terms of operating system services? So you can do the
I'm not aware of any of those, but most operating systems document this in some way or other in their own documentation. However, if you write software, you usually want it to be more portable than, it works with this version of libc. So there's a trade-off here to be more precise in your blocking or to be more portable. And I think that's a bad thing to have. It gives the wrong incentive.
And a question from the internet, please.
Yes, it's not really from the internet, but from one of the angels down here, so I'm going to hand him the microphone.
Yeah. So you mentioned that you mentioned using broker services to actually hand off opening files and how it doesn't help with processes that might need to open arbitrary files. Something we are doing with AppHammer is we are working on using broker services where it's actually the broker service which prompts the user for which file need to be open, which avoids having the service lie about needing to open the file.
When I say broker servers, I didn't mean it in a way that the operating system starts something, but I meant it that the application forks in the beginning, and then one of the two processes is the broker for the other half. So I don't mean it. I think if you want the admin to install anything so your app is more secure, you shouldn't rely on that because there will be mistakes made and you want your app to be secure in any event. So you should do it yourself as the programmer.
Microphone 8, please.
Hi, so isn't it a problem that most of these privilege dropping mechanisms require you to have super user privileges? Doesn't that create an additional time of vulnerability for a program that never actually needs super user privileges but would like to lock itself down?
I don't think most of the APIs do require super users. So Seccomp Filter doesn't, I think Tame and Pledge don't. I'm not sure about Capsicum, but I don't think it does. Change root does and jail does, because those are meant for different things. But if you write something like ping and you have an exterior mechanism to get your raw socket and you don't need to run as root, then you can use most of these APIs without being root.
Thank you very much. And Fefe, thank you very much for this talk.